Hello everyone, my name is Khatri. I'm a structural engineer. I'm pleased to provide this presentation for you on the Champlain Tower collapse, the building in Surfside, Florida. And I'll be presenting my notes and field observations today to share with you as to what's happened out there and what I think are some of the root causes that have resulted in this rather tragic event. So as an introduction, I want to be clear on exactly what I'm presenting. I am not working for any particular organization here other than myself and my company. I don't represent any government agency. This presentation is for information only based upon my experience in education, having been in this industry for over 39 years. And I'm providing my field notes from my first site visit on this project on June 26th, 2021, clarifying this as report number 1, as there will be subsequent reports to follow. So a few conclusions that I've been able to ascertain from the field visit is that, number 1, the building type is a flat plate concrete diaphragm with reinforced concrete columns. I'll be able to show you why I concluded that by looking at the damage photos. The age is 1980. That's been well published in the public documents. My conclusion is that this is a entirely gravity load collapse. There's no evidence of any earthquake or hurricane. There's no explosion. There's no lateral forces that are involved here. It's all gravity load collapse. And very important to note is that the existing conditions are very dangerous. There are existing cracks in the shear walls. I will show that to you in the photographs. And my total respect and honor to the emergency crews that are working there. They're using a system of laser surveys to monitor the existing building to make sure that they can at least get some sort of early detection, even though my opinion is that the site is highly unsafe, and I wouldn't advise anybody to be there, but I understand the importance of searching for loved ones and keeping the hope that they might be able to rescue some people. But I have to be honest, I think that the odds are diminishing by the hour, and the existing crew that's out there is definitely at risk. In this slide, we're looking at the crane that's helping with the recovery. You can see the existing structure on the right-hand side, and if you notice, there are horizontal and slightly diagonal cracks in that existing shear wall. That's what tells me that the building is under stress. It's experiencing surface cracks, and concrete is designed to crack first before it fails. So this is a serious indication that the building is at risk of toppling over and can collapse at any time. The people that are working on this site deserve an immense amount of credit and honor that they're risking their own lives in the interest of trying to find other people. And I'll show you these cracks up close in the next few shots. There's extensive evidence on the perimeter of the structure that shows moisture penetration, delamination of the exterior stucco surface. There's mold. Plenty of evidence to substantiate that this building has been experiencing water seepage for many years, perhaps many decades. And I'll show you a few pictures of that. But this is evidence on the existing structure right here that we're looking at. This is a close-up shot of some of these flexural cracks that are occurring in the shear wall structure. This is a sign of the concrete failing, and again, an indication that the building is under stress. Concrete is designed to crack first before it collapses. We have it built into our design codes that concrete will fail first and give warning signs to occupants before an ultimate collapse. And this is one of those warning signs. This is the building telling you that I'm about to fail, I'm about to collapse. So here again are signs of exterior mold, and the black shading there, the black discoloration indicates that there's water that's penetrated inside of that exterior surface, possibly into the wall itself. So this is not a good sign. This is the first signal to homeowners that if you see these black patches, that plaster needs to be removed and the concrete needs to be examined and the source of the water needs to be contained. And here again, similar evidence of exactly the same thing with the water penetration. It's throughout on every side of the building, and it's documented not just with my photos but also with previous reports. And here are the flexural cracks occurring at the base of the shear wall. The base of the shear wall has the highest load. Obviously, as you go to the top of the wall, that has the lowest axial loads. The highest axial loads are at the base, and these cracks are indicating an imminent collapse. The same thing we've been discussing earlier, and there's plenty of evidence on the surface of the wall. So this is a damaged column being picked up by this crane. And the concern I have here is that if you see the longitudinal steel from this column clearly bent, there's no evidence of any ties. Ties are circular, or in this case would be rectangular hoops that would tie that column together. And it's not observed anywhere along the length of the column. If you see the rebar is running straight through. And hoops are required, they're mandatory under most reinforced concrete construction, and definitely required in seismic and hurricane-prone zones. Now, this building being constructed in 1980 did not have the seismic, or in this case, hurricane-prone detailing requirements that were instituted after the year 2000 and in subsequent codes. But the requirement for hoop steel has always been there, and I don't see any evidence of hoop steel. So this could be a design defect or a construction defect dating back to the way the building was built. It's hard to say. I don't have a set of drawings to work off of, but just from what I'm seeing in this slide is not promising. It means that the building may have not been constructed correctly to start with, and that's a speculation at this point until we have further information. This is an aerial shot facing north. The east elevation is what collapsed. This was taken from a homeowner association next door and posted on the internet, and I've borrowed it under fair use law. And you can see here the enormity of the failure. It is a spectacularly large area that has collapsed. And by looking at this photograph, we're able to see that it is truly a gravity load failure. The entire section of the building collapsed, and again, if there were lateral loads, you would see a different type of failure. And you can see on the left-hand side with that garage level, the columns being spaced rather long. I'm estimating that they're spaced roughly 20 feet apart. That's based on experience because when you look at the parking lanes are generally 8 to 10 feet wide in these subterranean structures. So you have roughly 2 parking spaces, which will be roughly 16, maybe 17 feet. And so I'm estimating about 20 feet centerline to centerline from the columns, which is what I've used in my calculations. And you can see the flat plate slab construction sort of there on the bottom. There's another picture that'll give you a better indication, but that's what the purpose of this slide is. So in this picture, we're seeing the actual failure next to the existing building, and you'll see the areas that I've circled show the flat plate slab design with the rebar that was pulled out. It doesn't look to be very thick. I'm guessing between 6 inches to 8 inch max. It could be only 4 inches. It's definitely, I don't think it's a foot. And this is very common for this type of construction. There are no column capitals, and I'll explain that in a moment. And there are no beams. It's just flat plate connected to vertical columns. when we refer to flat plate construction with vertical columns, I've pulled this out of a textbook. The key difference is the vertical columns have no special increased thickness at the connection with the plate. The plate is connected directly to the vertical columns with no change in thickness. You can see the other options that are available out there have what are called column capitals. In some cases, beams. You'll see them in the lower left-hand diagram. And what that does is it gives us more thickness to work with to tie the floor slab to the column. We have more room to put in additional steel. But in this construction, with a flat plate directly connected to the column, there's no room to add additional steel. So the tie reinforcement to attach the floor to the vertical columns is very limited because you don't have a lot of thickness. So this is the reason that developers, structural engineers have specified this type of construction is for cost, because it saves money on the steel reinforcement, saves money on the construction speed. So it's pure economics as to why this is utilized. And here's a cross-section view of the flat plate connected to the column. You can see there are no capitals, there are no drop panels, and so this creates a very high stressed zone which has a high potential for failure. And I'll discuss that momentarily as to what I think the principal causes are of the collapse. And here is my diagram sketch showing for a one-story building, just so that we can understand what displacement will do to a one-story structure. You can see the points as I've labeled them, A, B, C, and D. If the column on the right, which is the column BD, deflects, in my sketch here, I've put it at 5 inches on a 20-foot span, then that will cause the deformed structure as you see it with my sketch, and it'll add additional secondary bending moments and increase the stress on the remaining structure, because there is nothing in the building code that requires architects and structural engineers to design for vertical settlement, especially uneven vertical settlement. There's no design criteria. We assume that the foundation remains stable and level within reasonable tolerance throughout the life of the structure. And if we have uneven settlement, that will put additional stress that the building's not expecting and could lead, along with the effects of corrosion of steel, to a collapse. And this is my schematic diagram showing how the multi-floor system interacts with the vertical columns. The two column lines that are shown here, it is imperative that they remain throughout the life of the structure perfectly straight. If there's any deviation in the alignment of these columns, it could cause failure at the floor slab to column connection. The loads are transferred, as you see in the middle floor sketch. Those are dead loads and live loads are transferred to the vertical columns and then taken down to the foundation. The shear diagram and the moment diagram indicate the areas of highest stress for bending and for shear force. The shear force stresses are highest where it meets the column, and the bending stresses are highest in the center of the slab. You need 2 layers of steel, a top layer and a bottom layer, in order to handle these 2 loads. From the pictures that I've seen so far, I'm not seeing 2 layers of steel. I'm seeing 1 layer of steel. Of course, there could be there. Again, I'm not making any accusations. I'm just saying it. I didn't see it in any of the pictures. But the thickness of the slab, if it is really spanning 20 feet, looks very minimal, very much on the lower end. And the only reason for that is to save cost. And if the rebar is truly corroded, then if you don't have enough embedment length, which is the length of steel required for it to tie itself to the vertical columns, then that would pull out and it would cause a total collapse of the floor system. This is my diagram showing typically how a concrete column will interface with a flat plate construction. You should have 2 layers of steel. You should have a top steel and a bottom steel. and that's to deal with the positive and negative bending moments, which there are negative bending moments when it interacts with the column, which means there should be a top layer of steel, and then there should be a bottom layer of steel to deal with the positive bending moments in the center of the span. And these are where these very high shear forces are transferred from the plate to the column. And that requires special reinforcement detailing per today's code, and doesn't look like that was there in this construction. At least I didn't see any visible evidence of it, and I think that this was a major contributing cause. If that steel is not properly tied to accept those high shear forces, which are the vertical loads, then that steel will pull out if the hooks are not in correctly, as I've shown. This is the area of high shear stress within that red circular dashed line. And these are my rough calculations, assuming a 20-foot span length from column to column. Here I'm just itemizing the loads. The standard residential live load capacity is 40 pounds per square foot. It hasn't changed. It was the same in 1980. They may have used an even higher load designed for this building because it's technically commercial, almost commercial, but it is still residential. So either 40 or 50 pounds per square foot. I've used the lower value, the standard value. If I'm using 6 inches of concrete slab, which I think is a reasonable estimate, then my dead load is 75 pounds per square foot, basic. If I add some mechanical and electrical to it, HVAC, I'm adding another 3 pounds per square foot. There's still additional loads here that I haven't accounted for. This is just to get a minimum estimation on what the design capacity is of these columns, and we'll calculate the total axial load at the base at the first floor. But using 120 pounds per square foot is my basic dead load plus live load. So here I'm calculating the axial load at the top of the first floor on the base columns, using a tributary area of 400 square feet per column, a total load of 120 pounds per square foot. I come up with a column load of just under 50,000 pounds per column per floor. And then adding that up for 11 floors, again, this is at the top of the first floor, roughly 528,000 pounds. And then I add up the roof. The roof is designed for 20 pounds per square foot. The 75 pounds per square foot, assuming a 6-inch slab on the roof. That adds about another 38,000 pounds. So I'm at 566,000 pounds at the top of the first floor. That is a considerable load on a single column. Just to give you a point of comparison, it's an empty Boeing 747 is roughly 450,000 pounds. So this is like a jetliner resting on just one column. This is without any hurricane forces, obviously no earthquake forces. And for those of you that own Chevy Suburbans, it's like 71 trucks sitting on one column. This is for just one column. So now if we look at the entire structure with 12 floors, each column having 566,000 pounds on it, you can see that if you have uneven settlement, and I've attempted to show this to you with a sketch here with the red line, where B and C are sinking, D and A are remaining stable, F is remaining stable, E drops, G drops. When you have uneven settlement, just like I showed you with that single-story structure, you will create secondary moments, secondary shears, in addition to the working loads that are already on the system. And if you have 566,000 pounds on that base column and the column tilts even slightly, the chance for buckling and failure of the ground floor columns is very high. And if the columns don't have any reinforcement hoops, no hoop steel, then the failure is imminent, because the column has literally no slack or no capacity to withstand that vertical and horizontal movement. And here I've repeated my previous sketch, except that now I've added the potential for lateral as well as vertical movement, because if the foundations sink, and this can happen, by the way, with either pile foundations or spread footing foundations, which right now I don't know what they built out there. I'll do a separate presentation to explain the effect of a pile system. But if you have even a modest rotation, you can see that if line A and C tilt to the right and line B and D are rotating to the left, just as a schematic, the chance of that column buckling increases substantially. And if you have 500,000 pounds, close to 600,000 pounds on that column, and it hasn't got the appropriate reinforcement, and it's also got corroded steel from the effects of salt water, then yes, it's going to buckle, and it's going to take the entire building down with it. And remember that none of these loads, which are the uneven settlement loads, are accounted for in our design process. We don't design for uneven settlement. It's not a criteria that we consider. We also don't design for a fatigue life or a corrosion life on the rebar. We assume that the concrete is going to protect that rebar. As you can see, in a saltwater environment, when you're close to the ocean, you need more protection. In 1980, the standard cover for concrete, for reinforcement steel, was around 1.5 inches. Today, if you're in a corrosive environment, it's a minimum of 2 to 3 inches, which would have increased the thickness of that slab to at least 8 to 12 inches, which obviously would have increased the cost. So the developers, the designers at the time, chose the most economical design. I hate to use the word cheapest, but more or less that's what they did. They did what was barely minimum required by code. And the building, having surpassed 40 years of service life, obviously showed indications of corrosion, showed indications of settlement. And these are the warning signs before a structure will fail like this. So what are my initial conclusions from this first report? Well, for sure the existing building is very unsafe and needs to be monitored, and hopefully we don't have a second catastrophe happen. Number 2, the structure has definite signs of water damage, mold, rebar corrosion. It's there in the previous reports. It's documented in the field. There's no doubt about it. It's been exhibiting this problem for many, many years, perhaps for 3 decades. Number 3, the flat plate slab with the concrete columns has missing steel elements, missing column ties, and possibly had weak connections, either by design or by construction. It's hard to say, but there's definitely evidence of that. So doing a root cause analysis on this structure, I see item A here, definitely a participating factor, steel reinforcement corrosion, which was documented by previous consultants. The settlement issue has been documented by prior consultants and is certainly a root cause, a contributing root cause of failure. There is the possibility also that the roof may have been overloaded during the repair process. I can't say anything about that right now. I don't have any pictures or anything to make a conclusion on item C, but the roof is the weakest structure. It's the weakest floor diaphragm in the entire building. And if they overloaded the roof, that could have led to a collapse, but I don't think it would have led to a total collapse. The total collapse is what changes the scenario here, because that indicates to me that it occurred from the base, which is obviously the highest stressed columns and should be the most reinforced. But it doesn't look like a roof collapse. It looks like a progressive collapse starting from the base. Water is definitely a factor. The question is, how did the water get there, or did it come from leakage? Did it come from groundwater? It could possibly be from a city water main. It would be very difficult to ascertain that because they protect their records and they don't share any of their leaks or information about their leaks. But that is something that definitely needs to be looked at. And of course, it could be a sinkhole, which we don't know yet. I don't see any cratering. If it was a sinkhole failure, there would be a crater line, and it would have taken down the rest of the building as well, I would contend. So I don't see that, but it's still something that needs to be looked into. So this is my first report on this topic. It's going to become a topic of national attention, I'm sure. It already is. Everybody now wants to know what happened, why it happened. I've given you my initial thoughts on this, and I've looked at many buildings in this classification. I will be having some update reports on this topic to talk about early warning detection systems. How can other building owners monitor their structure so that this doesn't happen to them? And a maintenance program for existing buildings to help repair these conditions so that, again, we can prevent this from ever happening. I'll also be discussing code provisions. Should we be making any changes? Should we be upgrading our codes to deal with this issue in the future? Should we require analysis for uneven settlement? I'll go into that. And, of course, more root cause analysis to discuss some of the topics that I brought up here. This is my first report, and there's more to follow. I do thank you all for your attention. I hope you got something out of this presentation. I thank you for watching. Those of you on YouTube, if you can give me a thumbs up, that would be awesome. And if you want to share this presentation with other folks, please feel free to do so. And on LinkedIn, I really appreciate all of the viewers that follow my notes and pay attention to the things I have to say. It's very much appreciated. Give me some questions, put them in the comments section. I'll do my best to get back to you, and thank you again.